The technique that I want to talk through as far as solving limited infinity problems using algebraic methods is what I like to think of as leading behavior. The part of a function that dominates the rest, the part that leads, and the point is that we can safely ignore the rest of the function at infinity. If we were thinking about doing stuff around 0, around like x equals 5, it's a different story. And the general advice that I have for you appears here. Higher powers of infinity dominate lower powers. So like infinity to the 5th, that's way bigger than infinity squared. Any infinity dominates any constant. So like infinity to the 1/2 is way bigger than 100,000. Any constant dominates any 0. So like 0.00001 as a fixed number is way bigger than something that's tending towards 0. And if I find that I have 0, say like 0 squared, that's going to be way bigger than 0 to the 5th. I'll say a little bit more about what I mean by that, because I'm not actually taking 0. It's actually very small numbers that are going to 0. So this is like 1 over 10 squared, comparing it to 1 over 10 to the 5th. Or like 1 over 1,000 squared. That's so much bigger than 1 over 1,000 to the 5th, right? Like incomparably bigger, to the point that like if the thing inside here is getting very small, this part here is just completely negligible. Like if I just have finite precision in my calculator, which I do, eventually I run out of precision and I can't even tell that I did anything. I'm going to get a bit more specific because that slide was pretty general. I feel like demonstration is the right way to do it. I'm going to do these two problems, and then I'll have you do these two problems, but we'll work through them step by step. So I'm going to use the technique of leading behavior in order to investigate what these limits are. And in particular, I'm going to look at the scale of the numbers, and I'm going to work on problem A right now. So pi, that's always pi. That's a constant. 3.1415926, blah, 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 blah. I've got a value here, sine of x, and it's guaranteed to be between -1 and 1. And then I have this one here. And this one here, that's going to infinity. So I've got leading behavior in this term right here. This is the leading term, or the leading behavior. So what I can do is I can say this limit is equal to the limit as x goes to infinity of 10x squared. And I can simply neglect the other terms because they're inconsequential. These are negligible in the face of something that's going to infinity. So my limit as x goes to infinity of 10x squared is equal to 10 times infinity squared, which is equal to infinity. So the 10x squared term dominates. And I'd like to verify that statement by again referring to my calculator. So let's plot this function together, shall we? 10x squared minus sine of x minus pi. And we'll go zoom standard. I don't know about you, but like that really feels like it's just a parabola to me. The 10x squared term dominates. You can't even tell that we had sine of x or pi involved in this function at all. I want to do that same process for problem B. I got some terms, and if I try plugging this in without getting more clever about my infinity stuff, it just looks like infinity minus 1 over infinity plus 5 indeterminate form. Infinity over infinity. And that's like, okay, like that's cool and all, but like that's not helpful. So what we're going to do is we're going to play the leading behavior game with this function. So we got some pieces that are going to infinity. This one and this one. And between those two, the 15z cubed part is going to be the one that wins. In the denominator, the 12z cubed part wins because You can add 5 to a billion all you want. You can add 5 to a billion all you want. It's like, I mean, is a billionaire getting $5 more matter? No, the billionaire doesn't care about $5. We're insignificant to that person. So I look at the leading behavior, and that lets me write that this limit is also equal to the limit as z goes to infinity of 15z cubed over 12z cubed. And then I'll do algebra, and we'll cancel. And this limit is going to be equal to the limit as z goes to infinity of 15 over 12 equals 5 over 4. So this function should go to 5/4. Why? Because the highest power matched, so those ended up canceling, and I ended up with just the ratio of those two coefficients. There's a really nice theorem in the textbook that describes this quite succinctly. Let's take a look at the plot, shall we? Y equals. Again, we're going to keep doing this because I want you to keep getting better at plotting functions. So let's. It's fun. It's funny. So let's plot function b. So open a paren 15x cubed minus x squared minus, I'm going to implement that as 1 over x. Now that looks good. Divided by, open a paren, 12x cubed plus 5. Plus 5. There we go. All right. So I'm going to take a second and pause and look at my function I entered. Looks correct. Yeah, looks good to me. So we'll go zoom 6. Oh, some interesting behavior on this function. Much as it's interesting around the origin, we don't care about what's happening at the origin right now. We care about what's happening at infinity. So let's pop over here to infinity, take a look. Looks like it's going to 1.25. Look at those y values, 1.23972. I mean, it really looks like it's going to 1 1/4. Looks like it's going to take a while for it to get there, but it's going to asymptotically approach that value. So graphically, I think we've shown now that this is in fact equal to 1 1/4. Which term dominates the denominator? Those x values are getting bigger and bigger and bigger. So it's going to be the x cubed term in the denominator, because compared to infinity, 5 is negligible at infinity. In the numerator, I've got 1, so I can conclude that this limit is equal to the limit as x goes to infinity of sine of 1 over x cubed. And now I'm going to plug in infinity, and on the next few slides, some suggestions for how to do arithmetic with infinity. So this is equal to sine of 1 over infinity. I'm not going to differentiate between infinity cubed and infinity. Generally, I'll just collapse them. This is set, and then 1 over infinity, that's 1 over a really big number. That's like sine of 0. 0 is 0. I would urge you to plot this function along with me and build that sense of how to see this graphically. Sine of 1 over, open a paren, x cubed plus 5. Yep, missed again. There we go. So I hope you have that entered on your calculator. And then we'll go zoom 6. There's some interesting stuff going on down there near the origin. Up here at infinity, I really don't care about that. This function smooths out, gets nice and low around 0 out at infinity. Of course, we always should be wary and suspicious of what's happening in any plot, because it is impossible to plot infinity unless you take some more math classes, in which case we can plot at infinity, which is not a subject for now. One thing that I would urge you to think about is like, what's up with the going on there? That's kind of interesting. We've seen that once before, haven't we? Yeah, we've seen that once before. There we go. Okay. We're doing the numerator right now. We're doing the numerator. I want to know which one dominates. One's got a really big coefficient in front of it. The other one's got a bigger power. Which one is it? Is it coefficients or powers that wins? So we're focusing our attention on these two terms right here. We're going to ignore the rest for now. And let's suppose that if z is like 10 to the 30, that's a pretty big number. Then z to the fourth is like 10 to the 120, and a million z cubed is like 10 to the 96. Yeah, so no, it didn't matter what the value of that constant was, right? This could have been a Googleplex, to a Googleplex. It doesn't matter. Eventually, z will become large enough because it's going to infinity that this term here will become overwhelmed by the other one. That is to say that the term z to the fourth is the leading behavior in the numerator, and this term here is negligible. Good, good, good. Let's do the denominator. Got a very tiny coefficient right here. Look how small that number is. 10 to the minus 50? That's like Planck length small. That's so small. And I've got 5 and 6. The question is the same as it was for the numerator. Is it coefficients or powers? Try, as you're answering this question to yourself, try setting z equals 10 to the 100 and compare z to the fifth and z to the sixth with a 10 times 10 to the minus 50 times it. Well, if z is 10 to the 100, then z to the 10 to the 500, because when you raise a power to a power, you multiply the powers. What do we get for the second one, this one? I have 10 to the minus 50 times 10 to the 600 is equal to 10 to the 550. Oh, and that's bigger. 10 to the 550 is bigger than 10 to the 500. Oh, okay. So there was some threshold beyond which z to the sixth became even larger than z to the fifth, even though it has this phenomenally low coefficient. So lesson is that coefficients don't matter for determining which term leads. In this case, the leading behavior of the denominator is that term right there. Let's go the distance and find out what the value of this limit is. By using leading behavior, we can state that this limit is equal to the limit as z goes to infinity of z to the fourth over minus 10 to the minus 50 z to the sixth. And now we should do algebra, and we'll cancel up top, and that'll turn into a 1, and we'll cancel down there, and that'll be squared. So this limit is equal to the limit as z goes to infinity of 1 over 10 to the minus 50 times 1 over z squared. And now we plug in infinity, and we should get that I have 1 over some number times 1 over infinity, and this part here is going to 0. So this is equal to 0. And if we plot the function, then we should be able to verify that graphically. Focus on in these problems here, these 4 problems. It was all about the power. All about the power. And all about comparing which power is bigger. You know, like in the numerator and the denominator, they're like canceled and I got a number. Here, I had a smaller number in the top compared to the bottom and I got 0. Huh. I wonder if there's a theorem in the textbook that says something about that.